Most of Chapter 8 deals with various analytic methods, such as the substitution rule, integration by parts, trigonometric substitution, integration using partial fractions, and so on. There are various analytic methods to find the antiderivative of a function. However, there are also many other functions which actually have no antiderivative, and so none of those methods will work in trying to find the integral. So when this happens, there are actually various numerical methods that we can use to approximate the value of a definite integral. So these methods basically use the idea that a definite integral represents some kind of area, and so to compute the area we just need to approximate it. Okay, so let's take a quick look at a small example to see how we can approximate integrals using areas. Okay, so suppose we want to approximate the integral from 2 to 4 of x squared dx. So I've graphed the function here. So the function is x squared. And so as you remember, this definite integral represents the area under the function in the interval from 2 to 4. So this area, the area of this region here. Okay, so the idea is to first subdivide the interval from 2 to 4 into a number of subintervals. So here it's specified to use 4 subintervals. Right, so we want them evenly spaced, and so we can do 2 more subdivisions here and here. Right, so now you see that there are 4 subintervals in between 2 and 4. 1, 2, 3, 4. And so this point is going to be at 2.5, and this is going to be at 3.5. And so we're going to try to compute the area of this region using rectangles, as we usually do. The idea is to use the midpoint of each rectangle. So to approximate each of these subintervals using rectangles, we need to determine how to create the height of the rectangle. So what we're going to do is we're going to take the midpoint of each region, so say here, 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 and here, use that as the height of the rectangles. So let me draw the rectangles in. So those are going to be my 4 rectangles. And the idea is that the integral from 2 to 4 x squared dx is going to be approximately equal to the sum of the areas of rectangles. Okay, so the area of each individual rectangle is just width times height. So let's first figure out the width of each rectangle. Since they're evenly spaced, the width of all of them should be the same. So we call it delta x. The delta x again is the width of each rectangle. And in general we can calculate it by taking the width of the whole interval and divide by the number of intervals. But the width of the whole interval is this width here, which is b minus a. and there are n subintervals in general. So b minus a is 4 minus 2, and in this case is the number of subintervals, which is 4. So 2 divided by 4 is 1/2, which is 0.5. Okay, so that's the width of each rectangle. Now we need to determine the height of each individual rectangle. Okay, so the height of each rectangle is given by the function value at each of these points. Okay, so the first midpoint is in between 2 and 2.5. So this would be the function value at 2 1/4, so 2.25. And then here, this is between 2.5 and 3, so that would be 2.75. So the function value at 2.75. Here, this would be the function value at 3.25. And then here would be the function value at 3.75. So those are the 4 rectangles. So again, the height of the first rectangle should be the function value at the first midpoint, which is 2.25. The second rectangle would be the function value at 2.75. Third would be the function value at 3.25. And the fourth rectangle is the function value 3.75. Okay, so now that we have the width of all the rectangles and the height of all the rectangles, we're ready to put it all together. Right, so again, we're approximating the integral from 2 to 4 x squared dx, and it's the sum of the areas of the rectangles. So the first rectangle would be f of 2.25 times delta x, so height times width, plus f of 2.75, so this is the second rectangle, times delta x. And then the third rectangle, f of 3.25 delta x. And then the fourth rectangle, f of 3.75 delta x. So again, this is the first rectangle, second rectangle, third rectangle, and fourth rectangle. So now we're ready to compute. Okay, so what is the function? The function is x squared, right? So we just plug it in to x squared. So we got 2.25 squared. Delta x is 0.5. This is 2.75 squared. Delta x again is 0.5. This is 3.25 squared. Delta x is again 0.5. Then we have 3.75 squared times 0.5. And then we can factor the 0.5 out. So this is 2.25 squared plus 2.75 squared plus 3.25 squared plus 3.75 squared. And we factor out the 0.5. So now let's calculate this. So this is 5.0625 The second term is 7.5625. This third term is 10.5625. Third term is 14.0625. And then this whole thing times 0.5. And then if you add it all up and then multiply, you'll see that the total is 18.625. So the total is an approximation again, so we get 18.625. Okay, so this would be the typical method used for the midpoint rule. But in this case, we can actually find the antiderivative, so let's see how this compares to the actual value. To the actual value. So let's compute it by finding the antiderivative. The antiderivative is x cubed over 3. Evaluate it from 2 to 4. So this is 4 cubed over 3 minus 2 cubed over 3. Then this is just 56 over 3, which is approximately 18.667. And so we're only off by about 4/100ths here. So that's what we call the error. So how much the approximation is off from the actual value. So the absolute error is how much this is off from the actual value. So the absolute error is about 0.042. So again, it's only off by 400. So this is a fairly good approximation using only 4 subintervals. And as we know, the more and more subintervals you take, the better and better the approximation you get. So let's also calculate the relative error. The relative error is to take the absolute error and then divide by the actual value. So 0.042 divided by the actual value, so 18.667, and this is approximately equal to 0.00225. And percentage wise, this is 0.225%. So again, we see that this is a fairly good approximation.